All right, let's take a look at exponential functions. We've talked about what a function is. We've talked about all kinds of functions in section 2.4 with our library of functions. We're going to add to that library of functions. So you should take out that piece of paper that has all those functions. The constant function, identity function, linear function, quadratic function, square function, square root, cube, cube root, etc. We're going to add exponential functions to them. I know you all know what an exponent is. It's a power. So an exponential function, f of x, okay, and I'll be consistent with this author. This author uses a to the x, where a is the base. And notice where the domain value is. This is a function in terms of x, and notice the x is located in the exponent. Well, we have two kinds of exponentials. We have either exponential growth, which means things are getting larger, they're increasing, exponential decay. So the equation's identical. Our base raised to a power. These are identical. The only thing that's going to change is whether this is increasing or decreasing. So it has everything to do with the base. Now let's think about this. If the base is 0, 0 to any power we haven't even talked about yet. All right? If this base is 1, 1 to any power is 1. 1 to the first, 1 to the second, 1 to the third. So for growth, this base has to be larger than 1. All right? So that's our first note that we need to make sure of. Our base is greater than 1. So it's 2 to the x, 3 to the x, 4 to the x. For it to be decaying, it's got to be getting smaller. It's got to be decreasing. So this base is less than 1, but it's still positive. So 0 is less than our base, which is less than 1. So think of a fraction, a positive fraction less than 1. Okay. So easiest way to take a look at this, and we're going to practice, is all right, here's our x, here's our function. All right, now, if we're taking a look and we're thinking about 2 to the x, that would be 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, etc. Right? We have 3 points that are on this graph. If x is 0, anything to the 0 power is the number 1. So this point here, 0, 1, is always on the graph. Then our next point that's going to be on the graph, I don't really want to put a value because it's going to depend on whatever the base is. If the base is 2, this would be 2 to the, I'm so sorry. If this is, what was I just thinking? If this is the number 1, okay, then this is going to be a to the first power, which is always a. So this point 1a is always on the graph. And then think about what happens if I put a negative value in the exponent. A to the negative 1 makes it a fraction. A to the negative 2 makes it a fraction. A to the negative 3 brings it to the denominator and makes it a fraction. So this point would be the point negative 1, 1 over a. And what ends up happening is we end up with this growth passing through those 3 points. So I'm going to write those points down again. Here's x. Here's f of x. If x is negative 1, I get 1 over a. If x is 0, I get 1. And if x is 1, I get whatever the base is. Our domain, all real numbers. Because no matter what value I substitute in, I'm going to have a value for that output. Now, if it's decay, I end up with these 3 values. I'm going to pick the same domain values. Negative 1, 0, and 1. And let's think about what happens if I take the number 2. If I take the number 2 and raise it to the negative 1 power. 2 to the negative 1 is 1/2. But if I take a fraction, right, less than 1, let's say I take 1/2 and I raise it to the 2 power, what ends up happening is it ends up being the reciprocal. So I get the point negative 1, and when I take 1/2, get the point 1 over a. Anything to the 0 power is 1. And if I take a fraction, any fraction like 1/2 to the 1 power, I just get the fraction back. But notice it's a fraction this time, so it's getting smaller. So the points are still the same. Okay, and notice this crucial point right hovering around the origin. It's not the origin anymore, but it's the point 0, 1. So decay graphs always follow this pattern of decreasing as I read from left to right. But notice if I take any fraction at all, 1 over 2, 1 over 3, 1 over 4, 1 over 5, if I raise them to a larger power, all they're doing is getting smaller and smaller and smaller. So when you add these into your library, all right, our domain for all exponentials, our domain is all real numbers. Because I can always put a negative value into an exponent and get a fraction. I can always put 0 into an exponent, anything to the 0 power is 1. I can always put a positive number, and I can raise something to a positive power. So the domain is all real numbers. The range, you'll notice, is always positive. The range is always from 0 to infinity. And we always have a horizontal asymptote along the x-axis, y equals 0, unless, of course, our graph has been shifted. Okay? So let's take a look at a couple of basic examples and notice what we end up with. So let's start with the graph y equals 2 to the x. Well, when in doubt, make a table of values. Okay? Or f of x equals 2 to the x. Notice what happens. I'm going to start with negative 2, negative 1, 0, 1, and 2. I'm going to expand a little bit farther so you can see what's happening. All right, well, if I substitute in negative 2, 2 to the negative 2 power is the same as 1 over 2 squared, so that's 1/4. 2 to the negative 1 power is the same as 1 over 2 to the first, that's 1/2. 2 to the 0 power, anything to the 0 power other than 0 is 1. 2 to the first, 2 to the second. So again, it follows that since the base was greater than 1, these points should be on the graph. At negative 1, we got 1 over the base of 2. At 0, we got 1. And at 1, we got whatever the base was. So it followed the same pattern. And if I graph this is exponential growth because the base value is larger than the number 1. At x equals negative 2, we get 1/4. At x equals negative 1, we get 1 over a. At x equals 0, 0 to the, anything to the 0 power is 1. When x is 1, we got 2 to the first. When x is 2, we got 2 squared. Now I'm going to write these out. Okay? Because I want to start with our 3 original points. Negative 1, we got 1 over the base. At 0, we got 1. At 1, we got the base of a. So notice we follow these 3 patterns. 1 over a, 0, 1, 1 comma a for the base. And then this will show exponential growth. We end up with a horizontal asymptote at y equals 0. So let's say I give you f of x equals 2 to the x minus 3. You might see it written that way. You're more likely going to see it written this way. It doesn't matter to me. We know that we can add in any order, so if you don't like seeing the constant number in front, just move it to the back. And now this tells me that this graph is going to shift down. So all that means is we're going to take this graph that we just did prior, and we're going to shift it down. Since we're shifting it down, that means we now have a horizontal asymptote at negative 3 because it's shifted down. And what I'm going to do is I'm going to use the transformations that we learned. And I'm going to go, okay, this is going to shift down. 1, 2, 3. So this horizontal asymptote is now, instead of at 0, this horizontal asymptote, which is what the end behaves like, is at y equal negative 3. From here, I'm just going to pretend that this is my origin. From here, this is my new origin, right here. My new origin, it just shifted down 3. All I have to do is graph these 3 points. Since the base is 2, okay, all I have to do is go 2 to the x minus 3. Actually, I think I'm going to do it this way. I think I'm going to do this. This is what we did in algebra. I'm going to go 2 to the x minus 3. See if this helps some of you. And I'm going to pick my same values. Negative 1, 0, 1. 2 to the negative 1 power is 1/2. 1/2 minus 3 is the same as negative 2.5. So at negative 1, I'm only a half up from my y-intercept. Only half up from my horizontal axis, my horizontal asymptote. At 0, 2 to the 0 is 1. So 1 minus 3 is at negative 2. Well, that makes sense because this should only be 1 up from my new origin. And at 1, I get 2 to the first, and 2 minus 3 is negative 1. So there are my 3 points. So it should look as if I've taken my exponential growth function and I cut and pasted it down 3. Right? I'm going to take 2 to the x again. Same graph. Because the only thing that might change is the value of the base. If this is a 5, this would be 1/5, 0, 1, 1, 5. Just depends on what the base is. Let's say I give you f of x. I'm going to keep the base the same since we just did this one. 2 to the x plus 4 power. And notice where the 4 is located. The 4 is located in the exponent with the x. So this is going to shift left 4. It's going to shift this entire graph to the left 4 units. Okay. So I could start with our 3 values, negative 1, 0, 1. We know there's always going to be 1/a. 1, and whatever the base is. And now we're going to shift left 4. Left is in the x direction, so I'm going to take all of my x values and I'm going to move left 4. So negative 1 is going to move left 4 and go to negative 5. 0 minus 4, 1 minus 4. We're doing the transformations exactly like we did in chapter 4. Chapter 2.4 rather. So this graph is going to shift left 4. So at negative 1, 1/2, that shifts to the left 4 and it goes to negative 5, 1/2. My point at 0, 1 shifts to the left 4. Our point that normally was at 1, 2 has shifted to the left 4. It's still exponential growth. Still has, notice these y values are getting smaller. It'll never hit 0, but it's going to behave like the line y equals 0. So exponential growth has these 3 values to start with. Now let's take a look at exponential decay. Exact same idea. It's just that we are decreasing. So I will switch the base. I'm going to switch the base. Instead of a base 2, I'm just going to make it a base 3. Instead of growth, I'm going to make it a decay. So I am going to go f of x equals 1/3 to the x. So the base is 1/3. So instead of, if I do a table of values, -1, 0, 1. We know it's decay because this is less than 1. So we know it's decreasing as we go to infinity. If I think about 1/3 to that power, 1/3 to the -1, I have to use the reciprocal. 1/3 to the 0, 1/3 to the first power. So again, same 3 points. -1, it's 1/a. It's the reciprocal, which was 3. 0, anything to the 0 power is always 1. Positive 1, 1/3 to the first is 1/3. And sure enough, it looks like our graph is decreasing with a horizontal asymptote at y equals 0. Same idea on the shifting, transforming, multiplying, stretching, reflecting. If I put a negative out front, that's going to reflect it over the x-axis. So I'm not going to go back through all of those transformations. We've done that in chapter 2. Okay? Now we can graph them and we're going to solve them. So we're going to take a look at solving exponentials next. And these are kind of fun. We're solving equations. All right. So before we solve equations, I want to remind you or show you a theorem that you may or may not be familiar with. And this theorem in mathematics says, okay, now we're solving exponentials. So if I give you a to the, here we'll do this. If the hypothesis, if a to the x equals a to the y. So if they're equal, everything about them is the same. If they're same, they're going to have the same value. So if they're equal, if the bases are the same, if the bases are identical, then the exponents have to be the same. So if I ask you to solve, and I'm going to start with one where the bases are already the same. If 5 to the 2x is the same as 5 to the x plus 3, and I ask you to solve for x, steps are identical to algebra. What are we solving for? X. Where is it located? In the exponent. Since it's in the exponent, the bases have to be the same. Since the bases are the same, we now know that the powers have to be the same. So this implies that 2x is the same as x plus 3, And now we solve using Algebra 1, and we're finished. So if the bases are the same, compare exponents. And somebody might go, well, what if the base, oh, here we go. Let me give you base e. E to the x squared equals 1 over e to the fourth. We haven't talked about e. E is Euler's number, okay? Euler's number. And I'll write that down here in just a moment. But that doesn't matter right now because our base is e. Is our base the same? Yes. So the first thing I'm going to do is I'm going to bring this up to the numerator. Anytime I take the reciprocal, this sign changes. We knew that if it was a negative exponent, we dropped it to the denominator. Well, if it's in the denominator and I bring it up, that's just a negative exponent. Well, now that the bases are the same, let's make the powers the same. All right, that implies x squared is the same as negative 4. And there you have it. We just use a little algebra. Now, as I mentioned, E is Euler's number. Euler was a mathematician a long time ago. You might say Euler, but Euler's number is the number E. And we'll talk more about this a little bit later, actually pretty soon. E is approximately 2.718. So it's really close to the number 3. So if you've got a graph e to a power, you can estimate it at a little bit less than 3. So e to the first would be 2.7. E to the second would be a little bit less than 3 to the second, so a little bit less than 9. E to the third would be a little bit less than 27. You get the idea, right? So now let's try some that maybe the bases are not the same. So let's say here's number 64 in your book. You don't need a calculator. In fact, you'll need to show me how you get your answers. 3 to the negative x equals 81. All right? Well, if the bases are not the same, write them the same. 81 is the same as 9 times 9, which is 3 times 3 times 3 times 3. So I'm going to write this as 3 to the negative x is the same as 3 to the fourth. Well, now that the bases are the same, the exponents have to be the same. Now we're finished. Done. Let's try it again. Here's 76. 9 to the 2x times 27 to the x squared equals 3 to the negative 1. Well, don't fret. Make all the bases the same. Make the bases the same. 9 is 3 squared. 27 is 3 to the third. And then we already have a base of 3. So I'm going to rewrite this. This is 3 squared being raised to the 2x power times 27 is 3 to the third raised to the x squared power. And the other side already had a base of 3. These are just laws of exponents, you guys. You learned in Algebra 1, you learned in Algebra 2, that whenever you have an exponential raised to a power, we multiplied exponents. So that's the same as 3 raised to the 4x power. We learned in Algebra 1 and in Algebra 2, whenever you have an exponent raised to a power, we multiply exponents. So that's the same as 3 times x squared. We learned in Algebra 2, whenever the bases are the same and you're multiplying, we add exponents. So I'm going to add 4x plus 3x squared. And now we've written it so that the bases are the same. So I have one exponential on this side. I have one base on this side. If the bases are the same, the powers must be the same. And now this is an Algebra 1 question. X squared plus 4x, bring the 1 to the left side, equals 0. Hold on. 3 squared, make sure I copied it right. 9 to the 2x, 27 to the x squared, 3 to the negative 1. 3 squared, so that's a 4x. 3 cubed, that's a 3x squared. Oh, I lost my 3x. There we go. Okay. There we go. Much better. Sorry about that. I just miscopied. So I brought this exponent has to equal this exponent. Now I'm going to solve this. You have a choice. You can factor, use the quadratic formula, complete the square. But if you complete the square, this has to be a 1, so you'd have to divide everything by 3. I'm going to factor. When we factor, and if you need factoring help, ask, look it up. If I factor, I end up with 3x plus 1 times x plus 1. From algebra, we now know that x is either negative 1/3 or x is negative 1. So there are going to be times you might get 2 answers. Okay. So if the bases are not the same, make the bases the same. I'll do one more of those. Trying to find one. 74. Take a look at 74, and we'll call that a day. Five to the x squared plus 8 power equals 125 to the 2x power. These are kind of fun. We know they're equal. So let's just make them look more alike. Can I write 125 as a power of 5? The answer is yes. That's 5 times 5 times 5. This stays the same, 5 to the x squared plus 8 power. I'm going to rewrite the 25 as 5 to the 3rd, and that's being raised to the 2x power. And then we know from our laws, rules, properties of exponents, anytime you have an exponent raised to a power, that's the same as multiplying those exponents. And now when we stand back and we look, we end up with 5 to a power equals 5 to a power. The only way that can happen, since the bases are the same, these exponents must be the same. And now the rest is algebra. You can choose to factor. What are factors of 8 that give you -6? So we end up with 2 solutions, 2 and 4. So the whole idea is get the bases to be the same. Then compare exponents using exponent laws. Okay? So there's a great summary on page 278. And a great explanation of Euler's number on page 275. They take it out to the 1/1000th power. And that's a look at exponentials.